Good morning. I am T. Rama Krishnan, Assistant Professor, Department of Mechanical Engineering, PSNI College of Engineering and Technology. For this video lecture, we are going to discuss hydraulic turbines. Under this title, we are going to cover first one, impact of jet and jet propulsion, and then layout of hydroelectric power plant and working of Pelton turbine. And method of construction of the velocity triangles. For Pelton turbine, and we are moving to determine the hydraulic efficiency of Pelton turbine. Finally, we go for discussing the significance of specific speed. Okay, these are the details we are going to discuss now. Now, turbines is a machine which converts the hydraulic energy into mechanical energy. This mechanical energy is to run the electric generator, because generator is directly coupled to the turbine shaft. So generator produces electricity. Thus, electric power produced by means of hydraulic energy is called as hydroelectric power. Okay. The advantage of hydroelectric power is that it's the cheapest one, because there is no fuel cost involved here like diesel in diesel power plant and coal used in the thermal power station. And the only drawback in the hydroelectric power is that it depends on seasonal raining. Right. Now we move into the discussion about impact object. Oh, okay. So turbines are classified into three categories. The first one is tangential flow turbine. Tangential flow turbine, and then radial flow turbine, and third type is axial flow turbine. So when the flow is tangential to the runner wheel, is termed as tangential flow turbine, which is also called as Pelton turbine. Pelton is the engineer. He was first developed this design, tangential flow turbine, hence is called as Pelton turbine. This turbine, which is suitable for the available pressure gauge more than 500 meter. Similarly, radial flow turbine, here flow is in radial direction, so the turbine planes are designed. This turbine is called as Francis turbine. Okay, this turbine is suitable for available pressure gauge in between 50 meter to 500 meter. Last category, axial flow turbine. The flow is axial direction so that the turbine plates are designed. This is called as like Pelton turbine, Kaplan turbine. This turbine which is suitable when the available pressure gauge is less than 50 meter. So this within this three type, we are going to concentrate theory behind the Pelton turbine, construction of the velocity triangle of the Pelton turbine, and then we are going to derive the hydraulic efficiency of this turbine. Now start with impact of jet. So impact of jet means it's a force exerted by the jet of water on the moving plate. For this, how to determine the force acting on that plate? For this, we have to consider one circular plate, curved circular plate, like this, okay, which is moving with the velocity of u. Now consider the jet of water which hits the moving plates at the middle, okay, jet of water which is strikes the plate at the center, so that the part of the jet is diverted left side, the remaining part is diverted to right side, okay. Now the velocity, absolute velocity of the jet, say V, area of the jet considers A, cross-sectional area of the jet. Now the velocity with which the jet of water strikes the plate is nothing but relative velocity of the jet, V minus u. Relative velocity is the difference between the absolute velocity of the jet and then velocity of the moving plate. It's a horizontal vector. Now the velocity of water jet relieved from the outlet of the plate, which is equal to the same relative velocity V minus u. This is considered by assuming no energy loss condition, so that say this is the slope of the velocity vector. You have to split this velocity vector into two components. One is horizontal component, is reverse direction, and vertical component, forward direction, upper direction. Okay. So how to find force exerted by the jet of water on the plate? For this, we have to use the impulse momentum principle. Impulse momentum principle, force which is equal to mass into rate of change of velocity with respect to time. For this, mass into initial velocity minus final velocity along the direction of the jet. Okay. For this, replace the mass in terms of density rho AV, density of the water cross-sectional area of the jet, absolute velocity of the water. For this here, because of moving jet, we have to use relative velocity and then initial velocity equal to E minus U and then minus of, to calculate the force along the direction of the jet. Horizontal component of this force equal to again V minus U cos theta. So after simplifying this, we'll get rho A V minus U whole square into 1 plus cos theta. So from that we can calculate the work done by the jet on the plate by work done per second, which is calculated by force into distance moved by the plate with the time. For that, we have to use velocity of the jet. With this, we find the work done as multiplication of velocity. Suppose this curved plate, which is fixed on the larger runner wheel at the outer circumference, like this. Now, velocity of jet at the outlet of this van, say V2. This is absolute velocity of the water jet, which is released from the outlet tip of this curved plate. For this, we can resolve this velocity vector into two components. One is horizontal vector, another one is vertical vector. Horizontal component of this velocity vector, which is termed as here VW, that is velocity of the valve at outlet 2. Similarly, the vertical component of this velocity at in upper direction, which is termed as VF2. This is velocity of flow. There are two terms used here for our convenience. Okay, this is one of the site of hydroelectric power plant. This consists of first one dam and pipeline and turbine house. This is one site of hydroelectric power plant. This consists of dam, pipelines, turbine in power house and then tail race. A dam usually constructed across the river. For power plant, dam is constructed at the higher elevation level. The pipeline, very large diameter of the pipelines are used. These pipelines are here called as penstock pipe, which is made up of either steel or reinforced concrete, and then turbine. So according to the available pressure gauge, the turbine is so selected, either Pelton turbine, Kaplan turbine or Francis turbine. And the last is tail race. This segment is tail race. This outlet channel of the discharging water. So this is the overview of the particular hydroelectric power plant. Right. This is the line diagram or of the power plant. Right. Here, this is the one of the turbine, Pelton turbine. This Pelton turbine, there is a runner wheel. Around the outer periphery of the runner wheel, there are number of buckets mounted. Hence, the bucket shape of the bucket is double hemispherical cups, which is mounted around the outer periphery of the runner wheel. Okay, that is Pelton wheel is the tangential flow impulse turbine. The power is developed on the runner wheel by impact of the jet of water strikes in the vanes, okay, so that the turbine starts rotating. So in this way the power is obtained, mechanical power, right. Now we are going to construct the velocity triangles for Pelton turbine. For that we have to consider cross section of the bucket like this. It's a section, cross section in top view. Right. With respect to this central axis, this is the slope of the bucket at outlet, which is called as deflection angle. The high velocity jet of water strikes the bucket at the middle. The part of the jet diverted into left way direction, the part of the jet is diverted in the right way direction. The absolute velocity of the water hits the center of the bucket at the middle, so it's considered as an inlet. It's released from the outlet tip of the bucket. This is outlet of the velocity of the jet. Now first draw the absolute velocity vector with respect to the inlet. Say AC E1, absolute velocity at inlet V1. Now this is measured by using the Venturi meter, which is attached to the end of the pipeline. Now consider tangential velocity of the bucket, because the bucket is mounted around the wheel, so that we can find the tangential velocity at inlet, say U1. This is the tangential velocity vector. Now absolute velocity is a horizontal component. There is no vertical component of the absolute velocity. So the horizontal component of the absolute velocity vector is equal to BW1. Now the difference between the absolute velocity and tangential velocity of the bucket gives us a relative velocity at inlet VR1. So in order to construct the outlet velocity triangle at the outer tip of the bucket, consider this slope with respect to deflection angle of the bucket. Now along this slope you have to draw outlet, that is velocity vector, relative velocity vector VR2, such that VR2 is equal to VR1 by considering the or assuming the no energy loss condition when the water flows through this bucket. From this we know the slope of this relative velocity at outlet, and then we have to draw the tangential velocity at outlet U2 by getting the resultant of this two velocity vector. This is in forward direction, tangential velocity similar to this one. Now by combining these two vectors, we will get the absolute velocity of the water jet at outlet V2. Say this angle is pi. Now we compute the velocity triangle by considering the compound velocity of the absolute velocity V2 at outlet. See, the horizontal line and vertical line. This horizontal segments gives us velocity component of V2, which is termed as velocity of the valve at outlet. Reverse direction. Here, this is velocity of the flow at outlet. Say this angle theta. So with this velocity triangle, we can easily determine VW2 and angle of the jet at outlet. So with the aid of this velocity triangle, we can easily calculate or determine efficiency of the hydraulic turbine. Hydraulic efficiency. Before that, find the runner power. Runner power. Runner power is nothing but work done by the jet of water on the bucket wheel. Here, first find the force acting on the bucket by the jet by using the impulse momentum principle equal to force along the direction of the jet x mass into rate of change of velocity with respect to time. Again, we know mass, the rate of change of velocity along the direction of the jet, v1 minus the horizontal component of the velocity, absolute velocity v2 is vw2 minus vw2 because of reverse direction. Also, we can replace v1 as vw1 because v1 is equal to vw1. So we can simplify this equation, mass into vw1 plus vw2, and then finding the runner power work done on the plate by the jet, which is equal to work done per second equal to force in the distance. Force is m into vw1 plus vw2 into distance moved by the bucket by time u. So this is the one equation. Similarly, we have to find the hydraulic efficiency. Hydraulic efficiency, eta h equal to, it's a output, it's a runner power, that is work done per second. Input of the per turn wheel turbine is kinetic energy of the jet, kinetic energy of the jet per second. So with this we can calculate the kinetic energy and work done. For work done, it's nothing but mass into velocity of the whirl at inlet plus velocity of the whirl at outlet into tangential velocity of the bucket divided by kinetic energy of the jet of water of m v1 square. Consider the absolute velocity at inlet. By simplifying the equation, we get the hydraulic efficiency. Hydraulic efficiency as 2 times of vw1 plus vw2 into u divided by v1 square. Here v1 squared is the absolute velocity of the jet. We can measure and directly use. vw1 also equal to the v1 for Pelton turbine. We can find the vw2 by using the velocity triangles. U is nothing but tangential velocity of the wheel. Okay. So now we are going to discuss the significance of the specific speed. specific speed of the turbine. Okay, it's nothing but it's a non-dimensional number which is used to relate or compare the different types of turbines. Okay, so in order to select the turbine, we can use this term non-dimensional number, and by using this number we can compare the prototype and model, right? So it is defined as is the speed of the turbine which is similar to the actual turbine that will develop the unit power under working under the unit pressure gauge. So how to derive this specific speed? Derivation of specific speed using the overall efficiency relation. The overall efficiency of the turbine which is equal to short power output divided by water power. Water power is nothing but rho g QH. Specific weight, rate of flow and pressure gauge. With this, rearrange this equation, power in terms of efficiency, specific weight, QH. With this, first three things are constant value, hence power is proportional to rate of flow and pressure gauge. Now rearranging this, power is proportional to rate of flow, is nothing but cross sectional area into velocity of flow again h. Now we know the formula for velocity of the jet at inlet. Velocity is measured by using this relation 2g. So velocity of the jet is proportional to root h. Okay, first replace this one, this v, again a h power 1 by 2 into h. Combining will get h power 3 by 2, and similarly replace the area. For this, we know the area of the turbine, it is nothing but width into multiplication of width with the diameter. For the purpose of dimensional analysis, replace this linear dimension width as a equivalent of diameter. Another linear dimensions you will make equal to proportionality, right? So this somewhat equal to proportional to t square, right? Now using the relation of tangential velocity, u is equal to pi d n by 60. From that, t is equal to 60u divided by pi n. Okay. Now t is proportional to this value. Again, we know that u is directly proportional to the velocity of the jet. Use the tangential velocity of the packet, which is directly proportional to the absolute velocity of the jet. Again, we know that velocity also equal to head. Velocity is proportional to root h. Replace this equation. T is equal to root h by n whole square. Now, instead of the a, put the value square root of h by n square. So power is proportional to area, that is h. Root h squared is h. Again h power 3 by 2 divided by n square. Now simplifying this one, as power is proportional to h power 5 by 2 by n square. Okay. Now power is equal to constant of proportionality k and h power 5 by 2 divided by n square. Now to find the the constant value k is the definition of the specific speed. Okay, so specific speed is considered with unit power when power is 1 under the head of equal to 1, n is equal to then speed of the turbine equal to specific speed. Specific speed, use this value 1, p is equal to 1, h is equal to 1 and n is equal to ns in this equation. So that p is 1, k, h is the 1 power 5 by 2 divided by ns whole square. Now k is equal to ns square. Okay, this is equation number 1, this is equation 2. Combine 1 and 2, we'll get the relation of specific speed. By combining the equation 1 and 2. Now power is equal to k n square into h power 5 by 2 divided by n square. Right? Rearrange this equation, ns n yes specific speed which is equal to n square is equal to n square p divided by h power 5 by 2. By simplifying this, specific speed is equal to, take a square root n square root of power divided by pressure gauge 5 by 4. So with this relation we can compare the different types of turbine with a specific speed. Right. So in this video lectures we covers basics theory of hydraulic turbines and types of hydraulic turbines, Pelton turbine, Francis turbine and then Kaplan turbine, and then we discuss the layout of idle power plant and then how Pelton wheel turbine works. With this idea we constructed the velocity drawings of the Pelton wheel turbine, and we also discussed the determination of the hydraulic efficiency and signification of the specific speed, and also we derived the specific speed for turbines. In addition to the theory discussed regarding hydraulic turbines, we are going to design Pelton turbine. Pelton turbine. That is, so let us suppose the Pelton turbine has to be designed under the pressure gauge of say 60 meter. The turbine runs at 200 rpm and it will develop the power say 96 kilowatt, and considering the efficiency of overall efficiency 85%. So pressure gauge 60 meter, speed n 200 rpm, power short power, that is P efficiency, overall efficiency. From this we can find diameter of the Pelton wheel and diameter of the jet. This is two important data. From this data we can design and select and specify all the dimensions of the Pelton wheel as well as buckets. Right. So how to calculate diameter of Pelton wheel? or runner wheel. Using the relation velocity, absolute velocity at inlet V1, which is nothing but coefficient of velocity into square root of 2gh. The coefficient of velocity considers 98%, 0.98 related to the nozzle, and square root of 2g constant 9.81 and head given that 60 meter. So the result obtained as 34 meter per second absolute velocity at inlet. By relating the absolute velocity and tangential velocity of the turbine wheel, runner wheel, we can calculate tangential velocity of the runner at the outlet, which is equal to 45% of absolute velocity at inlet. So which is equal to 45% of 34 meter per second gives us 15 meter per second. And so after this, by relating the tangential velocity and rotational speed of the turbine wheel, we can calculate the diameter of the runner. See, U is nothing but U is equal to pi d n by 60. So from that, diameter of the wheel, runner wheel, equal to 6 times of the tangential velocity divided by pi n. So it's equal to 60 into 15 meter per second divided by constant by speed is given at 200 rpm. With this, we get the result. Diameter of the wheel is equal to 1.4 meter. So diameter of the runner wheel is 4 bar. Similarly, diameter of the jet, water jet, diameter of the jet with respect to nozzle outlet. So D is equal to, so by relating the overall efficiency, eta naught is equal to power P divided by input power. Output is the short power, input is water power, rho g QH. First we calculate the discharge rate of flow, which is equal to output power divided by efficiency, specific weight of the water, and then get available get. Q again equal to power is given that 96 kilowatt divided by efficiency 0.85 into specific weight density 1000 kg per meter cube, G 9.81, and then head given that 60 meter. So the discharge is equal to 0.20 meter cube per second. So from this discharge, we can easily calculate diameter of the jet, that is diameter of jet. So Q is nothing but, using continuity equation, cross sectional area into velocity of the jet at inlet 1, 5 by 4 d squared area into velocity, rearranging for finding diameter of the jet, T is equal to 4 times of discharge divided by pi into V1 square root. So square root of 4 into rate of flow obtained as 0.20 meter cube per second divided by constant pi value V1 is 34 meter per second. So we'll get the result as T is equal to 85 millimeter. As already discussed, from the dimension of the diameter of the jet and the diameter of the wheel, runner wheel, we can calculate all the specification of the runner wheel as well as bucket specification in the terms of width of the bucket and depth of the bucket and other specification of the runner wheel. Similarly, we can also calculate or design the Pelton turbine using specific speed. Instead of the speed, we can also use the specific speed. So we already discussed specific speed. It's a non-dimensional parameter. Okay. So in the same way we can calculate it with using specific speed. So with this, in this video lecture, we discussed the impact of jet on the moving plate, and we discussed the construction method of velocity triangles for turbines and how to use and specific speed for selection of the turbines, and we discussed the design of Pelton wheel with one sample problem. Thank you.